Hello, and welcome to Group 6 final presentation of the Battlefield Effects Simulator Robot. I'm Nicholas Nakowitz, and I'm a computer engineer.
I'm Michael Rodriguez, and I'm an electrical engineer.
I'm Julia Kemper, and I'm a computer engineer.
My name is Jared Remkos, and I'm a computer engineer.
The Battlefield Effects Simulator Robot is a small-scale version of the robotic system that will be utilized on live fire ranges to support training realism and feed threat representation of pyrotechnics. This version of the robot will maneuver through rough terrain to desired location accurately and fire pyrotechnics when proper safety signals are met. The BES for the prototype will not be on top of the robot, but will still be in communication with it. The robot will interact with the BES to send the safety conditions for when it is clear to fire the pyrotechnics. The safety conditions include that it is in the correct location and that it is plus or minus 10 degrees level.
Our team has also had the opportunity to attend ITSIC, the world's largest modeling, simulation, and training event this past Monday and Tuesday to brief Army leadership, including the PEO, who is equivalent to a 2-star general, the DPEO, PEO Stride Chief Engineers, the UCF Board of Trustees, the Ensign National Director of the Pentagon, and other leadership. This has been such a great experience for us as students who are preparing to enter the workforce. We've received great feedback from all we presented to, and they're looking forward to the future of this project. Our motivation for this project comes from the government's derived need for a modular open system robotic platform that aligns with the Robot Operating System military framework and ecosystem. This robot is intended to increase training realism and feedback and improve safety measures during training by removing the human element when it comes to pyrotechnic handling. The overall takeaway from our team to our sponsors at PEO Stride is that this product will provide a rapid prototype and technical data package that can be leveraged by the Army to increase training throughput, improve safety, and reduce cost of live fire training. The main goal for this robotic system is for it to be utilized on live fire ranges to support training realism and feedback, threat representation, and pyrotechnic handling. Our objectives consist of the following. The robot will use LiDAR data to create a map of its environment. It will correctly navigate to its specified destination. The robot will detect obstacles in its path and navigate around them. The robot will ensure it is level plus or minus 10 degrees when it has arrived at its specified destination. It will ensure it has arrived at the correct destination. The robot will send signals to the GUI via the ESP32 that it is safe to fire, and the GUI will send signals to the BES to fire pyrotechnics.
Now for our constraints. Economic-wise, we were only given a budget of $1,000. And in the environmental constraints, the robot has to accurately navigate over rough terrain, hills, and holes. There isn't any social, political, or ethical constraint, but in the health and safety constraint, the team will not test with actual pyrotechnics due to the safety of the team. In manufacturing constraints, the main constraint there was the arrival of parts on time and if they were in good condition. There is no sustainability constraints, and our time constraint was the senior design timeline and the sponsor timeline.
All right, so here's the standards we used. So the first is a software requirements specification, and we basically use this to create unambiguous, verifiable, and complete requirements. And then we avoided terms like if possible in order to make them very clear. And then the software testing standard is what we used in order to troubleshoot the code. And we use that for a lot of like testing purposes. And then we also followed, since we used Java, Python, and C++, we used a lot of programming languages. So we made sure to follow the coding conventions for each respective language in order to make sure that the mentors and all the team can follow and understand everything.
And we're also following the rechargeable battery standard. This standard is mostly being followed due to safety requirements involving the battery. This will help us in lowering risk of accidents occurring with the battery and allows for, all the specs of the battery to be available for the users. For our specifications, the robot's dimensions is shown here, the length, width, and height. It weighs around 8 pounds, and the robot runtime has a bare minimum runtime of 1 hour and 44 minutes if everything's on full power.
This is an overall block diagram of our entire robot's design. It includes all of its components and the connections that aren't specifically hardwired. As you can see, on the outside, it is connected through an access point is the BES. And on the right-hand side of this diagram are two pictures of our robot.
All right, so here's an overall logic diagram of how the user, which has the tablet, and they interact with the robot. So basically, they tell the robot which site to travel to, and then the robot will calculate the optimal route, and then it will detect obstacles along the way. And then once it reaches the location by matching the GPS coordinates, it'll check if the ground is level. And then if it's safe to fire, then it will give a status message back to the tablet, and then the user can input the fire command and then fire the BES.
The accomplishments our team has achieved over the course of the last semester for this project can be seen on this slide. We'll dive further into all these during the course of this presentation.
This is the approximate distribution of the group. Anything labeled is the primary source. So for Julia was the primary Ross navigation, and anything with S is the second source, which would include Nicholas as Ross navigation. Hardware and physical design.
We're going to start off with discussing about the base of the robot. The base that we used was a pre-designed model that we purchased through Amazon. The base utilizes 4 treads and 4 motors to operate, so it's a 4-wheel drive. It also has several slots to attach components or extra platforms through the usage of screws. The other thing we added onto the robot was a 3D printed platform. We designed this platform in order to have more space for components on the robot, and it utilizes slots for multi-purpose, like either wires to go through those slots that we added or screws to hold the component in place. It also has 4 circular holes in the corners for, stacking platforms on top of each other or to screw it down in place. We decided on utilizing treads over wheels due to the following factors of it having better off-road capabilities and larger surface areas, which causes less pressure with the ground, which decreases the chance of the robot getting stuck in a hole or a rut. It also has better grip than standard wheels, which leads to less slipping.
Hardware, electrical components.
So we chose to use the Raspberry Pi 4B model as our processing unit. We ran Ubuntu Desktop on this unit, and it acted as our personal computer for this robot. And through Ubuntu Desktop, we downloaded ROS and all ROS programs, which is the operating system for our robot. The Raspberry Pi was also used to power the LiDAR and process the LiDAR data, power the IMU and process the IMU data, and power our PCB. And after our research, the Raspberry Pi was clearly the best option for our project because of all the documentation available regarding Raspberry Pi and ROS integration. And we were also able to easily obtain one from a reliable vendor for a fair price.
Now, the motor driver we used was the BTS 7960. This was used to power and control the motors. It's reliable for both low voltage and high voltage motors because it has a range of 6 to 27 volts. It was low cost and it was available from a reputable vendor. It also has a max output of 43 amps for motors, and it only needs 5 volts to operate on the logic side.
The LiDAR we chose for this project was the RP LiDAR A1, and the main reason behind this decision was due to all the official ROS documentation that exists regarding setting up this specific LiDAR with ROS and Raspberry Pi. The LiDAR was used by the robot to create a map of its environment it would be navigating through. And once the map was displayed in our ROS program, the LiDAR would then detect obstacles with the LiDAR in its path when navigating through the mapped environment. And we were able to do this using the RP LiDAR package that was developed by ROS. And you can see the LiDAR specs on this slide. The IMU that we chose for this project was the BNO 055, and this IMU was used in many other ROS projects, so there was also plenty of documentation available for this when researching the setup process. And this IMU was used to determine if the robot was level once it had arrived at its specified destination. And this was very crucial to our project because this is one of our required safety checks the robot must perform before the BES is able to fire.
All right, here's the GPS we used, which is another safety check that must be done in order to ensure that the robot's at the correct site location. So we use it to receive the longitude and latitude from a satellite. And then it's a very cheap, so that's like why we picked it, although it does have some constraints, like it takes time to like warm up and basically connect to a satellite, and then also can't be used indoors. And so the coordinates are transferred to the GUI, and then it's connected to the ESP through UART using GPIO pins.
We utilized two kinds of motors in operating this robot. We used motors with encoders and motors without encoders. The back motors does not utilize any encoders, and they use 12 volts for the power source, and they run at a max of 350 RPM. The front motors does use encoders. They run at 12 volts and run at a max rate of 100 RPMs. Now, the front row is connected in series with the back motors. The front motors are connected in series with the back motors in order to be able to operate both simultaneously. The front motors encoders also are used to keep track of how many rotations it undergoes so that it helps with nav stack transforms.
The printed circuit board. The printed circuit board that we decided to use is something that imitates the Arduino Mega 2560. Here's an overall schematic of everything that is involved on the PCB. We have the power LED, the actual microcontroller itself, the AT Mega 2560, all of our headers, our USB connection and USB to TTL, our power regulator, and our programming chip. As you can see, on the left is our new PCB that we actually used in the project, and our previous one on the right. On the right-hand side, you can see at D1, there is a switch that didn't have the proper footprint to match our key one footprint that we needed for our tactile switch. That is just one of the issues that we underwent. This is the PCB actually on the robot. And now these are all of our hardware challenges. The PCB footprint error that I already went over, and then also the PCB serial lines. The M8TX and M8RX lines for the FT232 chip were actually dedicated to the wrong serial port, and it should have been the default serial port, which was our TX2 and RX2. Not only that, but TX2 and TX4 needed to be swapped, so TX2 would be connected to RX4, something similar to our PCB have enough PWM pins, which was unfortunately something that we didn't have on our first PCB, and we overlooked with the encoders. So we had to add that onto our next board. The FT232 chip actually has compatibility issues with Windows, which was an easy fix. We just ended up using Mac OS and Ubuntu. And then the ESP32 board that we initially bought was dead on arrival, and therefore we had to buy a new board for it. The power design.
Now, in terms of power, here is the voltage requirement of each of our components and the maximum current they utilize. In this, the biggest usage of current were the motors, since there are 4 of them instead of just 1. So that current would be multiplied by 4. For our battery, we used a 14.8 volt LiPo battery. This is mostly just being used to power the motors, since the motors use the most amount of voltage at 12 volts, and it has the most amount of current to operate. The following is the specs of the battery, where it's 14.8 volts and it has a capacity of 9 amp hours. Its max discharge rate is 100 C.
These are our DC buck converters that we connected from our battery to our motor drivers to power the motors. We bought our buck converters instead of making because we didn't have enough time, and we wanted to focus a lot of our time on other aspects of our project. These are changing the volt from the 14.8 volts from the battery to 12 volts for the motors.
Here's the switch that toggles the power of the robot. And then once the robot is turned on, the ESP32 will begin running as a server to connect to the tablet.
This is the RAV power battery pack, and this is used to power the rest of the electrical system on the robot. It doesn't power the motors. It's just for all the other components. It is easy to use and is rechargeable. It has 5 volts. Its max output is 4.5 amps, and it has a big capacity of 16.75 amp hours.
Software design.
So our software design consisted of ROS, or Robot Operating System, as our operating system. we used the ROS navigation stack to perform environment mapping, robot navigation, and object detection. This involved various ROS packages, including the ROS LiDAR package, the ROS simultaneous localization and mapping package, and the RViz application to display all the obtained data. So ROS is a set of libraries and tools that help you build robot applications. So this includes drivers, developer tools, packages, and much more. The primary stack we used for this project was the ROS navigation stack. And this is a 2D navigation stack that takes in information from odometry, sensor streams, and goal pose, and outputs safe velocity commands that are sent to the mobile base. This requires in-depth transform configurations to be set up involving sensors and the motor controllers and encoders so that the robot's able to accurately keep track of where it is on the map and where it needs to end up at. So in order for the robot to accurately move around an environment, it must map the environment first. So this was done using our LiDAR data, a ROS SLAM package, and RViz. RViz is a visualization software tool for robots, sensors, and algorithms, and it enables you to see the robot's perception of an environment. So the image you see here is an example of a map that our robot created using its LiDAR data by moving around the environment. The robot's current location is depicted by the red and green V, which represents the transform configuration data. As the robot moves, the map continues to grow until it's ready to be saved and eventually used for navigation. And after the map is created, the robot's able to accurately navigate through its environment to the location that was selected on the GUI made by our team. The robot receives its velocity commands that allow it to move by uploading code written in the Arduino IDE to our PCB that the team created. The map was uploaded as an image in RViz so that the robot could use it as visualization and determine what the best path is. Next, the robot would use its LiDAR to detect any obstacles in its path. Our robot was consistently using the ROS navigation stack to keep track of its transform configurations so it could accurately identify how much further in its path it had and where it currently was. This was done using the SLAM ROS package and the RP LiDAR ROS package. And the image on the screen shows the robot using this LiDAR data when navigating in the environment. So the main challenge that our team faced when working on this software design was definitely the learning curve of ROS. ROS is a very useful operating system, but it's also extremely complex. There are many layers to how this operating system works. And although our team did create a working product that our sponsors were very happy with, I feel as if we had a few more months and to learn ROS, we could have an even more polished product. But thankfully, because ROS is so well known, there is plenty of documentation that could assist us with the issues we were facing. We also joined Discord communities and received help from other members with any ROS related issues.
Communication. This is the overall communication diagram. As you can see, everything lined with red is wired and everything lined with blue is wired. The Raspberry Pi is wired to the PCB and the PCB is wired to the ESP32, where the ESP32 and the ESP32 and the tracer tablet both connect to the router as an access point, where the router is connected to the BES via Ethernet cord.
All right, so here's the ESP, and we use a client-server architecture. So basically, the ESP acts as a server, and then it waits for the client, which is the tablet, to connect when they're on the same network, which is the router. And basically, so the GPS is connected through GPIO, and then it sends the coordinates to the tablet every 2 seconds. And then it also sends the launch status, which is determined if it's safe to fire. So it can receive a byte, which is like a character, which is like A, B, C, or 0. And the 0 means to basically stop, because in the GUI, which we'll see later, you can send, or whenever you like press travel, you can select the site, and that's what that means. And then it's also powered by the Arduino. And then the code is written in C++, and then there's the link to it. All right, so the GUI was created in Java using the Swing and JX Map Viewer 2 libraries. So it runs as a client and then connects to the ESP. And then there's 4 main tabs: the home, sensor, console, and map. So it's able to handle either the client or the server disconnecting and recover. So what I mean by that is basically, so like there's a good chance that like it's possible to like lose connection from the robot. And if that happens, then it's able to like continue running without like having to like restart the code. So like you can disconnect, reconnect on either of them. All right, so here's an example when it's ready to launch, because basically the launch status will send as a 1 to the GUI, and then it will be seen as that. And then here's a console which displays the connection status and then also like the coordinates when those come in. And then here's the map. And in this example, we press site A, so the robot's currently traveling to site A.
This is a BES tablet. It runs Windows 10, which allows us to convert the GUI into a jar file. It also runs the proprietary software that fires the BES. A test BES is used that does not fire actual pyrotechnic shots. It instead fires LED lights.
All right, so here's the main communication challenges that we faced. So the first one is that originally we were planning on using Bluetooth in Java to connect with the ESP, but the problem was the library was actually like really outdated from 2008, so it didn't work with like the current basically the current hardware that we had. So then instead of doing that, we decided to use sockets through Wi-Fi, and now since we're on the same network through the router, that works fine. And then another challenge was disconnecting gracefully. So basically to make sure that so like if the ESP or like say the robot's turned off and the tablet is still trying to like receive data, it won't know that it's disconnected. So I built in a timer to basically check like every 5 seconds. If the bytes are not received, then it will know that it's disconnected. And then another thing is identifying which component is in the buffer. So that's basically whenever the ESP is sending like the X coordinate and the Y coordinate, it won't know, it just sends it like as bytes. So what I did was basically make an identifier byte so that it knows which coordinate is which, and then it ends with a new line so that the tablet is able to like basically recognize it. And then another thing was, because the BES was so heavy, it was like 80 pounds, it wasn't able to obviously be directly on the robot. So we had to figure out a way to basically connect to it without being through Ethernet. So that's why we ended up using the router, and then the BES would connect to the router, and then the tablet and the ESP would also connect to the router. And then finally, we had a lot of difficulty running the jar file on the tablet. And this was because the tablet currently has like an outdated Java runtime environment. So we basically had to install like a new Java runtime and then run it specifically for ours, because they have also like other things. So we had to do that using Bash.
So the main concept that our prototype is testing is robot driving, the robot's connection with the BES and tablet, and identifying if objects is in the robot's path. For robot driving, the way we tested that was putting the robot in the testing site and have it move towards a specified location. While for identifying an object in the robot's path, the way we tested that was having the robot analyze the surrounding area. We also used an IMU to verify if the robot was leveled. And for connection with the BES and tablet, the way we tested that was by making sure that the BES was seen in the tracer range simulation program, as well as being fired through the command driver.
The next 3 slides, all of our, including spare parts and things that we need to solder on the PCB. As you can see, we actually made it under our $1,000 budget.
So because of the success of this project, our sponsors at PEO STRI have expressed an interest in continuing to sponsor UCF senior design teams to continue to evolve and expand this project. So some of the features PEO STRI has expressed interest in adding and improving include continuing to improve the accuracy of autonomous navigation, improve obstacle detection and clearing of obstacles that are no longer in the robot's path, camera integration to detect humans, and finally building this robot on a much larger scale. We're grateful to have been the first team that had the opportunity to work on this robot and lay a foundation that the future senior design teams will potentially work on.
Thank you for watching our final presentation. We look forward to answering any questions during our final presentation Zoom meeting.